Hi everyone. Today my group mates and I will be presenting light emitting diodes, aka LEDs. So my name is Rosandino and my group mates are Karen, Omar, and Damaris. So first, what are LEDs? So LEDs are light emitting devices. When a current flows through it, the quantum mechanics of LEDs can be easily seen through the movement of electrons within a diode in the form of photons in the visible light spectrum. So the structure of an LED can be broken up into three parts. You have the conductors, semiconductors, and insulators. So a conductor is where the electricity flows due to the overlap between the valence band, allowing a large flow of conductivity, whereas semiconductors allows for a moderate flow of conductivity and insulators allow for only low conductivity. And you can see that with these two pictures I have up on the screen. They're basically depicting the same thing, just in a different order. So you can see with the conductor, you have that overlap band that allows the large flow of conductivity of electrons. And then as you go down the list up into insulators, you see that large band gap.
In LED lights, there's typically creation of two semiconductors, and the semiconductor material is used as silicon. The silicon acts as an insulator, making the electricity harder to flow through, and it consists of four valence electrons. So you have to introduce a process called doping, which changes the electrical and structural properties. And doping is when you bring in impurities, you inject impurities into these semiconductors. The first type of doping is n-type doping, which is negative and has a surplus of electrons. And in this case, it would have five valence electrons. And p-type is positive, which has insufficient electrons. And in this case, it would have three electrons. What and it would create a hole, while the n-type has free electrons, and when combined they create a p-n junction, where the charges are able to diffuse and create an electric field.
Okay, so semiconductors, the NP junction, the whole construction is connected to some source of energy, like a battery. You can picture it like an electrical circuit. The electrical circuit is pumping electrons into the N-type side of the device, and it will combine with the holes in the central junction or central region, junction point. What happens is eventually there will be a huge concentration of holes and in the central region, and the electrons will need a place to go. So a free electron in the conduction band approaches a hole in the valence band just because of opposite charge attraction. And this is where electron hole recombination can take place. A free electron drops down in energy to fill the empty spot in the valence band lattice, meaning that the electron is transitioning from a higher energy state down to a ground state. There's a release of energy. We know what conservation of energy is. That energy must be converted into something. In this case, the energy is emitted as a photon, and that photon will have a specific wavelength that corresponds to its energy level. This phenomenon can be represented with the familiar equation of the energy of a photon, the one you see on the slide. I also included a diagram to represent the electron moving from the conduction band to the valence band and the emission of a photon.
All right, so for color variations in LEDs, as you guys may know, in the visible light spectrum, different wavelengths produce different colors of light, and that's basically the same idea for LEDs. The changes in wavelength are what allow LEDs to produce different colors of light, and the light emitted from an LED is related to the specific transition between electron quantum states and the semiconductor. By changing the band gap in the semiconductor, we can directly change the color of an LED. For example, blue photons contain greater energy, hence a higher energy transfer is required to produce blue light, whereas a red photon will require a lower energy transition. And this can be seen in the bottom right picture, where well, they all basically contain the same semiconductor. The only difference is changing the band gap. So we change the band gap from, if we have a large band gap, we're going to produce blue photons. If we have a small band gap, we're going to produce red photons. And it's also important to note that not all emitted photons will have a wavelength of visible light. So we could also produce photons or are, for example, infrared. And the changes in energy determined by the energy band gap between the conduction and valence band will only emit visible light if the difference between the band gaps corresponds to a photon wavelength in that visible light spectrum. And another way to change the wavelength is by changing the semiconductor. So on the left, there's a chart, and it just has like different semiconductors, and it just shows how they produce different wavelengths of light. And yeah. All right, so that pretty much concludes our presentation, and these are just some memes we decided to put at the end, so enjoy.